it going?
We can move out of the table.
See you.
Yeah.
Perfect. You like that color?
Like I've seen a bunch of people do it. Yeah. So
Tell me based on Craig or this or that.
I tried to do it.
the most incredible.
How are you?
Good. Oh, we can go strong.
Yeah.
Still reminded that where all those windmills are now and the ultimate
Yeah.
where the hell's
Oh yeah, that's right. The Rolling Stones concert.
Yeah.
Pulling an early with those straps.
So I grew up in Tracy.
Yeah.
On the other side of the Altamont, and my dad's high school was in Liverpool, so it's a good pass every day.
Wow.
Yeah.
Berkeley.
That'd be hilarious.
What year was that? Was that like
70?
Hey! You excited?
Oh, yeah.
How did you start here?
2010.
after the
Yeah. I've been swatting it away from me.
The angle is good.
Probably.
He's mostly gonna be over there. But then it's
We were in part of the
Oh, I remember it happened. Helped organize Thank you.
Do we have something?
Yeah.
Hi, John. How are you?
He was not on the student committee then.
Okay, yeah.
Yeah.
He was. He went to my work hearing. John, good to see you.
John, you know Gianluca's
Oh, John came by and talked about
That's right. That's right.
mega program.
Team Perry's and
Lower the shade too, so you don't get distracted. Did you pick your final one?
Yeah, so we're, Did you get that in? It'll be long.
All right, if you wouldn't mind taking your seats, we're going to get started with the public portion of the thesis defense of Santiago Padron. I guess I'll like to say a few words about Santiago, where he comes from, and some of those things. So he came to us with a bachelor in physics from the University of Wisconsin, and a bachelor in aerospace engineering from the University of Minnesota. Early on in our lab, he was very, very interested in gust responses for various different things. He was an early contributor to the development of the SU2 framework. And the gust response things that he was interested in were in the context of these vertical axis wind turbines, in the context also of a program that Gianluca, myself, and Mike Eldred at Sandia were actually putting together. So that led to interest in multi-fidelity methods, how to combine high and low fidelity, how to apply those methods to energy production. And for the last almost 3 years now, he's been working on an NSF-funded program that it's a collaboration between us and Brigham Young University, with one of the former students of our department, to enable the optimization of extremely large wind farms with many, many different turbines. And the idea there is to enable many of the turbines, but also to enable the fidelity of the modeling of those turbines to actually go quite a bit higher. So he's going to be talking to you about some of those things today. The committee for the defense is being chaired by Professor John Dabiri from Civil and Environmental Engineering, and from right to left, Professor Per Enge from Aeronautics and Astronautics, Michael Kokendorfer from Aeronautics and Astronautics, and Gianluca Iaccarino. And I have to say that on a personal level, it's been really fun to have Santiago around the lab. As you can tell, even now, even though he may be nervous, he's always smiling. So the guy radiates fun. Never a sad face. I don't know if maybe it's because I was walking into the lab and he just goes with his smile. He's also a very, very, I think, a generous person with his time for others, but also helping a bunch of young kids in the IAA Young Astronauts program to learn about aerospace engineering and be inspired. If you notice, right next to his desk, he has this really nice notebook. I guess a third grader or second grader.
Yeah, that's a relative of mine, but
It's a relatively young guy, so very good. But no, he's always doing this, and it's actually been very nice. One thing he doesn't know is my wife always tells me when he sees that, he's like, he reminds me of you when you were young. So she sends you her best wishes for your test today, and without further ado, I'm going to just turn it over to you to talk about what you've been working on. So.
Okay, well, I've heard that from other people sometimes too, but hopefully one day I'll be as awesome as you. Well, yeah, thank you for the nice introduction. I'm very happy to be here and share and thank you all for coming. I'm very happy to be here and share the work I've been doing at Stanford over the last years. As Professor Alonso alluded, the application I'm going to be talking about is optimizing a wind farm, in particular the layout by moving turbines around. And I'm going to be talking about methods that we've developed to make sure we can do this optimization efficiently. So wind energy is a very important source of renewable energy. In the United States, it generates about 5% of the total energy. California, around 7%. In some states, such as Iowa, it's up in the high 30s. And in Denmark, it's over 40% of the wind energy. The Department of Energy has a goal set to try to reach wind energy penetration, 20% of total energy by 2030. And I hope that's my goal too, and I think the goal of a lot of you in the committee. And we're moving in the right direction. So if we look at the amount of new power capacity installed, in 2015 in the United States, 40% of it represented wind, while 60% of it was other. And this holds over the world. If you look globally, the power capacity installed was 50% of all the new energy installed. So again, it's growing quite rapidly. If we look at just the dark blue bars is the cumulative amount of energy in the United States. And roughly it's doubling every 5 years or so. And all the energy we're building, and mostly looks like this. So it's a very large wind farms. The wind farm, again, is just a collection of wind turbines, where the wind turbines are very large. A particular turbine, they're over 100 meters, and a modern turbine has over 100 meters in diameter of the blade. Just for reference, the tower is probably as high as the Statue of Liberty from the base. And each one of these wind farms, each one produces a lot of energy. A particular one like this can produce up to 1,300 gigawatt hours, which is enough to power 100,000 homes. If you sell the energy, you can get like a yearly revenue of around 200 million. So if we change the amount of energy it produces, the annual energy production, by 1%, that represents 2 million extra revenue. So small modifications to the layout can have a large impact. So that really relates to the question, are we building optimal wind farms? So in order to answer this question, there's a lot of things we have to look at. The wind farm optimization problem is highly complex. First, if we want to optimize a problem, and we have many design variables, such as the turbine characteristics, turbine's position, number of turbines, so the optimization is very large. We also have the flow field. It's very, very complex. So in order to hope to get some of these interactions, we need high fidelity models. And just while I'm talking about these interactions, so here we can see turbines operate in the wake of other turbines. So this is non-ideal. So grid-like layouts like this, they're not necessarily optimal because of this effect where the turbines operate in the wake and they won't operate as well. And the other thing that we really need to account, and it's not really been properly accounted so far, is the actual uncertainties in the problem. So there's a lot of uncertainty and what exactly are the wind conditions, such as the wind direction, the wind speed, the turbulence in the wind, and so forth. So we're going to be focusing on this last one. So the goal here is to enable the use of high fidelity models in both the analysis and the optimization of wind farms, because if we can start using high fidelity models, that can really help us in building these new farms and building them optimally. And as I said, we'll focus on property accounting uncertainties. So this is how my talk's going to go. First, background, where I'm going to talk about the different components of wind farm optimization. Then I'll talk about the annual energy production, which is the amount of energy that a farm produces. That's what we're going to optimize. Some previous work in wind farm optimization and my contributions. Then I'll talk about the weight models needed to model the farm and different fidelity models we can use there. Then I'll talk about uncertainty quantification. So really a method we're using now to properly account for the uncertainties. I'll talk about, in this framework, what is currently being done, basically amounts to the rectangle rule of integration. And I'll talk about polynomial chaos, how we've developed it to apply it to wind farms. And then I'll talk about extensions of polynomial chaos for multi-fidelity and gradients. And this is one of my contributions. And then for the results, I'm going to be looking at the AEP convergence results. So basically looking at how many simulations we need to properly compute the AEP. And the idea is we want to reduce that number so we can run a few high fidelity simulations and get a good estimate. If we want a higher efficiency of getting it with less computational cost, we can use a multi-fidelity we will use the multi-fidelity method to do that. I'll show that in results, and then finally I'll show you some wind farm optimizations. So the different components of a wind farm optimization, or of any optimization, you need an objective function. Our objective function is going to be the annual energy production, how much energy the farm produces. Another common objective in wind energy is the cost of energy. So how much it costs you to build or operate the farm in a year divided by the annual energy production. So maximizing the AEP reduces the cost. We're going to focus on just maximizing the AEP directly. The problem has constraints, and this type of problems we have, the constraints are geometric, such as the area of where the farm is, like the boundaries, the separation between the turbines, how the turbines are connected through the cable length, and other constraints such as noise. Design variables, here we have lots of choices, so the problem can be very large. We have the turbine position, the turbine type, number of turbines, more of a passive, and then we want to do something active, we could have the yaw angles of the turbines for a wind farm that's already built. And then uncertain variables, again, we have the wind conditions, direction, speed, turbulence, so forth. But we can also consider parameters of the models as uncertain variables, and I'll talk about that more in detail later. And then finally, we need a model in the optimization. And then these type of problems, you normally have two models. You have an engineering wake model, which is fast to compute, and then a computational fluid dynamics model, which is a higher fidelity, but you need more computational resources. And again, we're going to focus on properly treating the uncertainties here in the problem. So just a deterministic optimization, what we have is an optimizer sets design variables to the model, and you get an objective and a gradient. A gradient if you're using a gradient-based optimizer. If you add uncertainty in the problem, so now we have an optimizer, design variables into uncertainty quantification box that I'll describe in a second, and then we optimize on some probability or on some statistic of some kind. And then we have an inner loop which we compute the statistic. So for this we have the uncertain variables, and then we get a response of the model, the gradient response, and we have this double loop, nested loop situation. In the context of sort of wind energy, what these the design variables are the turbine positions, the uncertain variables are wind conditions. The model outputs the power. We average the power, and we get the AEP, the power multiplied by the number of hours of the year. So again, the goal here is to enable wind farm optimization under uncertainty. So the challenge is both optimization and uncertainty quantification are computationally expensive. So each one of these will require many calls for the optimization and then the uncertainty quantification to the model. So just to give you a sense, we might need 100 optimization iterations for a problem with like around 50 design variables. like a couple hundred UQ samples for a problem with a couple uncertain variables to compute the statistic, and then so totally we'll need around 20,000 module evaluations. And this is like doing something very well. So there's a lot of model evaluations in this problem, so we were trying to bring the cost down. So really the solution, we're going to be focusing on the uncertainty quantification block here. We're going to focus on really how we can provide the statistics more cheaply with less high fidelity simulations. And for that we'll be using polynomial chaos, which I'll talk later. The other focus is if we add another model, if we have information from different models, how we can use that to also give us a better estimate of the EDP. So that was the components of the wind farm optimization. Just briefly, what is the annual energy production? Again, it's just the expected power produced by the wind farm in 1 year. So, and we normally measure it in gigawatt hours. The expected power, we take the expected value of the power, where we have uncertain variables, such as wind direction, wind speed. For the results I'm going to show, I'm going to assume that they're independent. And then you have a probability density function associated with it. And these you would get from data or someone who took data of the wind conditions. So currently how this expected power is computed, it's really as a simple average, which amounts to the rectangle rule. You have a likelihood that the wind comes from a direction, and you evaluate the power there, and you add those up. And then you get an estimate of expected power, and hence an estimate of the AP. I'm going to show you how we can use polynomial chaos, which is an uncertainty quantification method, to estimate the AP with a lot less simulations. Just some previous work on wind farm optimization. Again, the goal is trying to enable the high fidelity analysis and in the optimization of the farms, considering a large number of design and uncertain variables. So this review paper here looked at, up to 2014, pretty much all the optimizations on the wind farm, and none of them were using high fidelity models. So, and very few of them were actually using gradient-based optimizers. And most of them have small design variables. Again, it's a challenging problem, but everyone's working towards improving this. Kusiak in 2010, he started looking beyond these grid-like layouts, where before all he did was a separation between the rows, and then let the turbines float around so you move in XY space. More recently, Gebrod and our collaborators at BYU, they performed a large optimization with over 100 design variables, and what they did here is they've developed a wake model that provides gradients, such that they can use gradient-based optimization. All of these, you don't really properly account for the uncertainty, or they calculate it in very simplistic manners, but they're building up towards this being able to use the high fidelity models in optimization. So the contributions, I just want to tell you up front what they are as we go. So the first one is really we're looking at a whole different way of computing the AEP, what was normally being done in the wind farm optimization community. And I'm going to show you how we tailor the use of polynomial chaos to efficiently compute the AEP. Second, we've extended polynomial chaos to include the gradients in the multi-fidelity to both compute statistics and the gradients of the statistics, so we can use these in the optimization. And lastly, I'll show a successful demonstration methodology for numerous large wind farm AP computation layout optimizations. So different layouts, different distributions, and so forth. Okay, so that was a bit of the background. So now the wake models, we need to compute the power. So this is sort of the setup we have again, and we're focusing on the model part now. So how do we compute the power of a wind farm? So a wind farm, I'm going to abstract it this way. So it's to scale. Each dot is the diameter of the dot is equivalent to the diameter of the blades, sort blades. So in order to compute the power for the farm, well, we need the power of each individual turbine. So you add them up, and you get the power of the farm. How you get the power of an individual turbine? So that's 1/2 the air density times the coefficient of power for a particular turbine times the area times the velocity at the turbine cube. So for a known turbine, you know what CP is, you know what A is, you know what rho is, and then CP is the function of UI. So what's an unknown is what is the velocity at a particular turbine. So we know what the velocity is coming in, for instance. Well, it's very hard to draw a straight line with, with a laser pointer. Yeah. So you have the velocity coming in, and then you're trying to find what the velocity is inside of the flow field. For that, you need a wake model. So the wake model will compute the velocities inside the flow field. And one thing to notice, I'm not even going to try with the laser pointer, is, so it takes some, right behind the wake, there's a velocity deficit, and then it takes some time for it to recover. So when there's turbines bunched together, a lot of times the turbines in the back will be operating in slower velocity regions and producing less power because of this. But we need a wake model to compute it, so I'm going to talk about different wake models that exist. So again, there's engineering wake models. These are fairly simple. We'll be using this one, the Flores. It has an incoming velocity, we have a rotor, and then it has 3 zones of different velocity behind the rotor, a near wake zone, a mid wake, and a far wake, and then it has different spreading rates that control how these wakes develop. And these are tuned based on either experiment or higher fidelity simulations. And then on the other end of the spectrum, we have computational fluid dynamics, particularly large eddy simulations. And this is a simulation done by Gutt and Professor Lele here at the department. What they're looking at is they're looking at trying to find a reduced order model for these large simulations. Right? So a particular large simulation like this, you run on the grid, could have hundreds of millions of elements. I think this one had over 300 million. And it could easily run a million CPU hours. So I did a little calculation for fun. If you want to optimize the wind, like a wind farm running a high fidelity simulation such as LES, in order to find the optimization, it's probably going to consume all the energy that the wind farm produces in a year. So this is very expensive. So people are working on both trying to have the accuracy of the high fidelity models, but with lower cost. And what we're trying to do is reduce the number of the actual high fidelity simulations that you need to get a good optimum. I just want to give you a sense of how wake models compare. It's not like one will give you the right answer. There was a project set out by the International Energy Agency where they asked people to simulate a few cases and like with different wake models and see how they do. So in this case I'm showing it's a turbine. We're going to look at the spreading angle behind it, and we're going to measure the velocity at a particular distance behind it. So that's what I'm showing here. So this is the velocity deficit at 5.5 diameters downstream, and we have different models trying to approximate the field data. And like notice, like right behind the turbine at 0 direction is where you have the least velocity, and then it recovers. So here there's kind of 2 classes of models, CFD models and engineering models. And I'll show you tabulated results of this in a second. So if you look at different regions, 2.5 diameters downstream, 5.5, 8.5, and look at the error compared to experimental data. In the near wake, all the models do fairly poor, 15 to 20% error. And this is because most of them are not actually modeling the unsteadiness in the problem. They're not modeling the rotor itself. They're using some sort of actuator disk. As you go further out, which are distances that you'll likely see in the optimization. Turbines are usually around 5 diameters apart or so. The models are producing around 5% error, and there's not much of a difference between the high fidelity and engineering models, usually because the engineering models get tuned for particular conditions. So that's for a single turbine. If we look at a wind farm, again similar. This is part of the same study. So we have the inflow direction, as the wind can come from all 360 degrees, and we're looking at the power produced by the farm, power efficiency, so how much it would produce if it was operating, all turbines were operating out in the wake. And the yellow dots are data. So the numerical results, what they're going to do, they're going to average over little sectors of either 5 degrees or 30 degrees. If you were to average the whole curve, you basically will get the AEP. So what they found is if you average a very small sector, like over like a one sector of 5 degrees, and you compare the error to the experimental error, you get a fairly large error here. And then if you do a larger sector, the error is closer to, it's lower. But note that engineering models actually do fairly well here. And if we average over the whole thing, which will be the AP, which they did not show in the study, the errors would probably be likely similar. So normally you're not predicting the AP by like around 10 to 20% wrong. And another thing what I want to point out, they don't have results for the LES for the 31 sector because that would have required running many LESs, and as I said, that's expensive. The point here is we have multiple fidelity models, we have different classes of models, and we'll be using the engineering models because they're fast to run, and we can still show how we can use multi-fidelity within them. So we'll be using two sort of engineering models of different fidelity. The Flores model that I showed you before, it has these 3 wake zones, and then a Jensen model, which was the first model proposed. It just has one zone behind the rotor, reduced velocity, and it has one parameter that controls the spread of the wake. So we want to give you a sense of how these models, the response of these models, and how, because this will help us understand how well they'll perform when we combine them for multi-fidelity. So for this particular layout out here, if we look at the power response as we move around with wind direction, and then the Flores, the high fidelity is blue, and the Jensen, the low fidelity is orange. So, and the 0 degree is straight north, and you go clockwise. So if you look, let's say at 270 degrees, the wind is coming from this direction, the turbines are kind of aligned, and that's why you get these big drops of power produced. A couple things to notice here is there's large oscillations in the problem because of the if we look at the correlation between the models, it's around 0.82 for this particular case. And if we look at the difference between the models, what the difference function looks like, you can say it's a more complicated function, but the variance of the function is smaller. So if you're going to use 2 models for multi-fidelity, a couple things you're looking at is like, are they correlated? And is the model less complex, or does it have less variance? And like these models show these characteristics, so they'll be helpful for multi-fidelity. So this was the power response versus wind direction. If you look at it versus wind speed, for a particular wind direction, this is a simpler response. It's fairly cubic. The power goes, again, as the velocity cubed. So it's cubic up until you start reaching, particular turbines start reaching rated power, and then eventually the whole farm reaches rated power, and it flattens out. And the difference between the models again are highly correlated for this case. And then this is a difference function again, which it's much smaller magnitude than the high fidelity and the low fidelity. Oh, yeah. And like this is some of the previous work we did with the Gus, where we showed if you have multi-fidelity models and sort of have these characteristics, they'll be helpful. So now we talked about the models. I'm going to go into how we compute the AP. So basically, we were in this block. Now I'm going to talk about this block. So uncertainty quantification, I've been using it. I realize maybe not all of you know what it is. It has 2 components. One is the characterization of the uncertainty, which is the question, basically, what is the uncertainty variability in the inputs? So for this, you go and measure, get some data, and then from that, you can get probability distributions. So I'm not really, I'm assuming someone gives me a probability distribution. We got some data, and they told us what particular probability distribution is for a particular wind site. The second part is their propagation. So this is what is uncertainty in the outputs given the uncertainty in the inputs, or the variability in the outputs given the uncertainty in the inputs. And one way to quantify this uncertainty is by mean of statistics. So we're going to be using the AP, which is like a mean statistic to compute this. There's different methods for the propagation. The simplest one is Monte Carlo. or Monte Carlo type methods. Another one, if you're computing the AP, we can do direct integration. It's an expected value. And people are normally doing what amounts to the rectangle rule. And another approach would be to use a surrogate model of some kind. And we're going to be using polynomial chaos, which is kind of like an ideal surrogate in a sense. It has polynomials that are orthogonal to the uncertain variable. And it has nice properties. So we'll be talking about that. Just sort of visually what the methods are doing if you're trying to approximate the speed response. With the rectangle rule, we're just using little rectangles to, and the more rectangles you use, the better approximation you get. And with polynomial chaos, what we're trying to do is trying to approximate the function with a polynomial. There's a couple issues that you saw, like sometimes when you approximate a function with a polynomial, especially if it flattens out, you'll have these wiggles and oscillations. So we need to make sure we regularize those and make sure those are not there. One of the ways to do it is just, once we know that the turbines get flattened out, we can not evaluate all the way out to there. So briefly, just the rectangle rule. Again, this, if you've done in calculus, you've probably seen it. You're just going to sum up, if you're going to evaluate the expected value, you're going to sum up little rectangles that show our base delta psi, and then times the power and the density. And a lot of times you know what the PDF is, so you can integrate that exactly. So it'll be basically this weighted sum. This is what's currently being done. And the AP, if you want the AP, it's the expected power times the number of hours in a year. So now I'm going to talk about polynomial chaos. So some previous work, a lot of the original work in polynomial chaos was an intrusive method, so it modified the model we were using. What I'm going to be talking here is non-intrusive, so it doesn't modify the model. One of the Husder used polynomial chaos. There's two ways to compute the coefficients of polynomial chaos. I'll go in detail. Like one is either a quadrature based or regression based. Here they showed how to use a regression base to compute the coefficients. And a lot of these applications are from aerospace, like in safety problems, or simpler functions. Mike Eldred, a collaborator, he looked at polynomial chaos and getting the coefficients with a quadrature approach for some simpler problems. Eldred showed how you can use the polynomial chaos for in a design under uncertainty framework. Ning and Eldred showed for simple models how we can combine multi-fidelity in the polynomial chaos. Then with Eldred, we extended this in the 2014 paper for a larger problem. And then recently, in 2016, Pilar did multi-fidelity based on regression, and we've done that as well, and I'll be talking about that. So I'm going to go into the theory of polynomial chaos. So this is going to be some math. It has a strange name, but don't worry, it's not too complicated. And the reason why I'm going to go through it because some of the contributions are in extending it, so I want to make sure you understand what it is that it does. So the idea here is we're going to approximate the function, like the power that we care about, as a polynomial expansion where we have coefficients and we have polynomials, and these polynomials are orthogonal. And the expansion has a nice property because of the orthogonality of the polynomials with respect to the uncertain variables, namely that you can get analytic statistics. So the mean, or the expected value of the power, is the 0th coefficient. And so you have a 0 coefficient, you can get the AEP. I'm going to be showing the variance as we go along because in previous work we did a robust optimization, and so I want to show you how we get those statistics as well. But for this particular work, we're mostly interested in the mean. So there's two components. There's the polynomials and there's the coefficients. The polynomials again are orthogonal, and they're orthogonal with respect to the probability density function. This is just what orthogonality means. And one of the nice things is families of orthogonal polynomials, such as Hermite or Legendre, have corresponding weight functions that correspond to probability distributions of like common probability distributions. For instance, a normal distribution, the ideal set of polynomials is Hermite polynomials. For uniform is Legendre polynomials. If you have a distribution such as a wind condition, which you're not sure what that might look like, well, you'll set up and it's not going to be a uniform, it's not going to be a normal. So you need to make sure you construct orthogonal polynomials for that, and you want to make sure you construct them in such a way that they remain orthogonal. So we'll numerically generate them. So I just want to, there's different ways to numerically generate orthogonal polynomials. Graham-Smith is probably, if you've done linear algebra, you remember it, but it's not stable numerically. So we'd be using the stages procedure. And I just want to show you what sort of the orthogonal polynomials look like for a different weight. So I have a uniform weight, the PDF. So if the wind direction came uniform for all direction, or a weight for the Princess Amalia wind farm. So that's what the wind distribution is for that particular site. And if you look at what the polynomials look like, they're like this. The first polynomial is always a constant, it's 1, then we have a linear term, quadratic, cubic, and so forth. And these are the actual polynomials. So the Legendre polynomials, are you familiar with them? And then the numerical polynomials. So these will vary depending on what the actual weight function is for the PDF, the problem. So that's how you get the polynomials in the problem. So how you get the coefficients. So again, I said there's two methods. There's a quadrature method and a regression method. And in the polynomial case, there's a lot of names for this. But I'm going to be referring to them as quadrature and regression. And it's not just me who refers to them quadrature and regression. Some people use it, and people try and simplify the language of the method. So briefly, in the quadrature approach, we have our expansion. We take the inner product on both sides. Again, this I'm just reminding you what the inner product here is. We use orthogonality of the polynomials. We solve for the coefficients, and we have a formula for the coefficients here. It's kind of similar if you're doing like getting like a Fourier mode. You end up with a similar equation. If we're only focusing on the AEP, so if you only want the mean statistic, it'll be the 0th coefficient. The equation simplifies. The first polynomial is 1, and the first product of polynomials is 1 as well. So the quadrature approach, what you're doing is you're going to evaluate this integral with quadrature. And then again, this is proportional to AEP. Particular, we'll use Gaussian quadrature because we have the orthogonal polynomials for the range, so we can get the Gaussian weights. And in contrast to what is being done, again, the rectangle rule, so we're using a higher, if you use polynomial case based on quadrature, you'll be using a higher order quadrature approach to compute the coefficients. The other approach, which is more useful for this particular type of problems, and we found to be more useful even in the low dimensions of the problem. Low dimensions and uncertain variables, I'll get into that in more detail. So we set up a linear system. Each column of the V matrix is a different orthogonal polynomial basis evaluated at different points. So phi0 all the way to phi n. And then we have a set of powers. So here, we take some samples. Normally you want to make sure you cover the space properly. You can do a Latin hypercube sampling is what I'm doing. So you can do some sort of design of experiments to get the samples. You get the samples, and then you have a degree of polynomial choice, which you can then solve for the coefficients. Different ways to solve this. You can solve it with least squares, or you can do some sort of regularized least squares, and people call this compressed sensing. And one nice thing in this approach is if for a given number of samples, if we use cross-validation, we can really make sure we can find what the best polynomial order is for the approximation. And I have more details in the thesis of how we would go about doing that. And just a reminder what it is that we're trying to do. We're trying to compute the coefficients because the coefficients gives us the statistics of the problem. So the mean is the 0 coefficient, and the variance, again, is the sum of the other coefficients. So I'm going to briefly talk about some extensions we've done to polynomial chaos, to both for multi-fidelity and to include the gradients. So we have the problem here again, where for the model, again, we have if we have more models that have a high fidelity model, but if we have a low fidelity model that we also evaluate at particular wind conditions, we get the power of the low fidelity model. And what we do is inside the UQ algorithm, we combine the responses of the different fidelities to provide an estimate of the high fidelity AP with a multi-fidelity estimate. So that's the idea. We want to combine the results from these two models to get an estimate of the statistic. So we're going to map what that looks like. There's different ways to go about it, or like different correction functions. The particular correction function we're going to use is an additive correction. So the correction, we construct a correction function, which is the difference between a high fidelity and the low fidelity response at a particular set of win conditions. This is what we had before. We can have an approximation of the high fidelity model. We can do a polynomial expansion up to a certain number of terms. I'm just showing an expansion. This is terminology. An expansion for the low fidelity in all terms, and we can also do an expansion for the correction function. So the idea here with multi-fidelity is to approximate the high fidelity power with adding sums of the low fidelity, adding expansions of the low fidelity in the correction function. So now we're going to have a new estimate of our high fidelity with the expansions of these two models. If we write out what those are, we have, again, it's the sum of the coefficients. And the idea here is, so for the n corrected, which requires high fidelity evaluations, because to get the correction function, you need to divide the high fidelity. You want that to be lower than the number of high fidelity evaluations. That'll save you cost. And the idea is you can get the better approximation by using a lot of low fidelity samples, and it gets more information here to help you approximate the problem. And then if the low fidelity model is fairly cheap, you can do many more low fidelity simulations to help you accelerate to get a better approximation. And then briefly, if you want to get the statistics, such as the AP, it will be now the sum of the first zero coefficient of the low expansion and of the correction expansion. Okay, so to get the gradients now, what we're going to do is the polynomial now, expansion depends on design variables, x. Same formula as before, but now the coefficients are a function of x. So the mean is also a function of x, and the variance is a function of x. So we're going to take the gradient of these. So the gradient of the AP will end up being the gradient of the zero coefficient with respect to the design variables. The gradient of the variance, we take the gradient of this, we'll end up with, it's 2 times these are product of the polynomials, times the coefficients, times the gradient of the coefficients. So in both cases, we need the gradient of the coefficients. And as we can compute the coefficients with 2 methods, so with quadrature and regression, we can compute the gradient of the coefficients as well with both methods. So looking at quadrature, we have the coefficient equation from before, just written in inner product terms. We take the gradient. The gradient will go through the integral because the design variables are independent from the uncertain variables. And we end up with, well, this is the gradient of the coefficients. We substitute those for the gradients and the gradients of the statistics. And we end up that the gradient of the AP is proposed, the number of hours times this, which is this is just a notation, it's the inner product of, now not of the power, but of the gradient of the power, so the expected value of the power, of the gradient of the power. Substituting in the gradient of the coefficients for the variance equation, we end up with another equation that again has an inner product or an integral that we'll need to solve with quadrature. So we solve these with quadrature, and we will get the estimates of the statistic of the AP and of the variance. But for both of this, we also need the gradient of the power with respect to the design variables. So ideally, you would have a model that provides these analytically, such as is the Forest model, that provides these gradients, or you could do finite difference. The nice thing is a lot of high fidelity models have, where people are developing adjoints on them, so you can get access to these high fidelity gradients. And then sort of what I talked about here about extending polynomial chaos, multi-fidelity for the gradients, we presented at last SciTech. So how to get the gradient statistics from regression? This is new, and this was we're going to publish. We're going to send out to a journal soon. just want to remind you, so if you're getting the coefficients with regression, it's through this linear system. So we'll take the gradient. It goes through the matrix because it doesn't depend on the design variables, and we end up with this large problem. But we need to solve the problem for multiple right-hand sides. And so we'll solve that, we get the solution in the first column of the matrix, solve it, get another one, and combine all of this first row, and we end up with the gradient we need to get the gradient AEP. If we combine, and then lower part of the matrix, we have all the solution to get us the gradient of the variance. Okay, on to the results. So I want to show you the results. I'll show you for some representative layouts. These like grid layout, these are what are kind of normally being built. Grid layout, an Amalia layout, that's an actual farm that's called the Princess Amalia. What a typical optimized layout looks like, and the random layout, you can use random layouts to start an optimization. So we have kind of grid-like layouts and non-grid-like layouts. I'm going to show results for all of these type of layouts. So again, we have two methods to compute AEP, and I'm going to be comparing both of them. So we're going to use the rectangle rule for one, and then for the other one we use the polynomial chaos. So for this particular layout here, the Prince Amalia layout, we're looking at the error and the AEP as we increase the number of samples. The blue line shows the results of polynomial chaos with regression. The other line with the rectangle rule. We're showing a 1% error. That's kind of standard of how well you expect to compute the AEP. And this is for a particular set of realizations. So I'm gonna show you the results in average in some sense. It helps visualize sometimes the results better because you don't have too many of these peaks where you estimate it well and don't estimate it as well. So in order to do that, I'm gonna show you an ensemble of results. So for instance, if I was considering these 8 directions, I could consider a slightly rotated other set of directions, and I'll get a response that looks like this. If I average over 10 sets of directions, and then plot the average error, this is kind of what it looks like. So I'll be showing the results that are average error because it's easier to see what's going on. And again, what we're going to be focusing on is like when do we cross the 1% mark, and when basically the other method crosses the 1% mark, how many samples. That's one way of the results we're going to look at. The other one here, I'm showing the variation of those 10 sets of samples, and as we increase again the number of samples, and we can see with polynomial chaos with regression over there, even the worst and best estimates we get, which represents a band, after a couple hundred simulations that are within the 1%, whereas here it takes much longer until you get there. And these are kind of just representative results that I'm showing. The nice thing is that it works for all layouts. So we have the grid layout, the grid-like layouts above, and then an optimized layout and a random layout. So these layouts have higher variance because of the power, and then you have regions where you're operating the wake, so they're harder to estimate. You need more samples for both methods. But you can see the polynomial chaos, you can compute them with less samples. So if we kind of look at, again, when we cross this 1% error, we can get a reduction of the number of samples we need to compute it. For this particular layout, 6, this time around 8, this particular around 10, and they're fairly equivalent for this particular error. So one of the nice things with by formulating the problem in this way is now we have this expected value. We can take expected value with other uncertain variables, not just wind direction, wind speed. For instance, the wake parameter. And this is just, I want to show you how you would easily add other parameters and show the results. And the results I'm going to show is for the low fidelity model. So the results are, polynomial chaos does better independent of modeling. And again, the uncertain variable now is this wake parameter described by a uniform distribution. So again, similar set of results, and same grids, same two methods that we're comparing, and we see similar factor of sample reduction around 8 times, 10 times, 10 times, or so 7 times. And I guess what we're comparing again is when do we cross 1% here and when do we cross the 1% mark for the other method. So by using polynomial chaos, and especially with based on regression, we can show that we can get significant factor anywhere from 5 to 10 reduction in the number of samples, which is helpful if you're going to be using high fidelity, trying to do high fidelity computations. So now I'm going to talk about how we can accelerate that even more with multi-fidelity. The idea again here is we're going to use different fidelity models to get an estimate of the AEP. And let's just jump. Oh, and I'm going to be using 625 low fidelity samples as we change the number of high fidelity samples in the convergence. So this is similar to again. The plot now only goes up to 200 samples, high fidelity samples, and we're using 625 low fidelity. Blue line's multi-fidelity, the orange line's high fidelity, the best high fidelity results. And again, we can see that for any number of high fidelity samples, we estimate better the AEP. And again, if we look at sort of the factor of reduction we can get, for this case around 3, 2, 3 again here, around 5. So you reduce not just on the error, but if you're looking at the variance of the problem. Left multi-fidelity, right high fidelity. We've also reduced the variance because we have information from the low fidelity model gives us information on the response of a function. And we look sort of at the variability reduction for all the number of samples. It's about 3 times, and 2 times, and 2 times. So by using multi-fidelity, we can further accelerate how well we compute the AEP. If we put both of those together, we get large savings, or like order of 10 at least compared to what's being done, or more. So now I want to talk to you about the wind farm layout optimization problem. So let's formalize the problem. So we want to maximize the annual energy production as a function, and our design variables are the XY positions of the turbines. And we have uncertain variables, which are going to be the wind direction and the wind speed. And we have some constraints in the problem, namely that the turbines stay 2 diameters apart. We have 60 turbines in the problem, and that they stay within the convex hull of the original Amalia boundary. So it stays within all these boundaries. And we're going to be using a gradient-based optimizer. First thing I want to show you is a deterministic optimization. So this is the case where we know exactly that the wind will come only for one direction for the year and at a particular speed. And the way I'm showing you this is to show that the problem has multiple there's multiple solutions. So we have different starting layouts here. I'm going to run the optimization. And these are sort of the optimal layouts I obtained for this particular case. So again, the wind only comes from one direction here. So it's constrained by the boundary of this one. So the turbines do what you think they would do. They go out to meet the wind, and then they try to get as far back, the other side as far back as they can from it. And then they set up on, sort of not on a grid behind each other, so kind of this triangle shape. This again to give you a sense of what, so you'll find multiple solutions, and actually if you look at the efficiency of the farm, they're fairly equivalent. Well, they're nearly equivalent. So now a problem where you actually have the wind comes from all directions and different speeds. I just want to show you the optimization so you get a sense of how the turbines move around as the optimization progresses. If we look at the final layout compared to the starting layout for the Amalia, the darker dots are the final layout. So here, I mean, it's not, it's hard to say like there's going to be an obvious solution where the turbine should go. But one of the things that you can see that the turbines do, if they can move to the boundary, they try to move to the boundary, and they try to spread out as much as they can and try to avoid straight lines between them. If you're looking at the optimization history, so if starting from a layout that is pretty optimal already, it usually takes us around 100 to 200 optimization iterations. And for those, we're computing the AP. And again, we're computing the AP with 225 samples. If we look at the increase from this layout that was already optimized, we get a 2.2% increase. And this, the one point I want to argue here is, I can talk about more later, but that's increased with the method we use to compute the AP as we perform the optimization. If we run a Monte Carlo study for both the initial layout and the optimized layout, we find that the AP only increased by 35%. And no one ever reports this. They only report what they find with what their method, like how much you got better. But in some sense, here, like when you're optimizing, you're not actually considering all possible directions. So once you do the Monte Carlo, then you're actually looking at directions, and then because the optimizer exploited some weaknesses in the model. If we look at starting from a random layout, so one of the things I want to show is starting from a random layout is good because the turbines can move a lot more. So if you're trying to find the best layout, you can do this. And they actually move to fairly similar positions than the one I had before. So a lot of them go to the boundary again, and then that's the shape. If you look at the optimization history, usually starting from a layout that's kind of crappy like this, I mean the turbines are basically overlapping there. It'll take you larger number of optimization iterations to converge. The AP increase 17%. If we measure with Monte Carlo, it's 16%. So the optimized layouts, even if we start from a good layout or a bad layout, we end up with similar APs. That's what I wanted to show. So it's good even starting from a bad layout. Problem here is you require more evaluations. Getting back to comparing how you can do the optimization for different methods. All the results I show with polynomial chaos-based regression, and now I'm showing like the optimals you get if you compute the AP with the rectangle rule or with a fine rectangle rule. Starting from the Amalia layout, starting from random layouts. And this is just to give you a feel of what the layouts look like. I'll show numerical results in the next slide. So what I'm showing here is the number of samples I used to compute the AP that I use in the optimization, and then the improvement I found as measured by Monte Carlo. So one thing to notice, if we use about the same number of samples with polynomial chaos and the rectangle rule, we're going to find layouts that are better. And again, like for this case, 1% better, which is significant in AP computations. And then furthermore, even using less, like about a third of the samples, polynomial chaos compared to the rectangle, we still end up finding layouts that are better. So kind of in summary for the optimization section, polynomial chaos also works better here. With less number of samples, we can find optimums that are better than the rectangle rule. And then the layouts themselves are kind of non-intuitive what the optimal layout should be. And then starting from random layouts, you can find good layouts as well. So let's finish up with the contributions and summary. So first, again, it's I've showed you a whole different way to approach the problem of computing the AP in wind farms. And then I've showed how you can use polynomial chaos tailored specifically for this type of problem. And with this, we show we can get accurate AP computations with anywhere from like 6 to 10 fewer simulations than what is currently being done. Next, I showed you how you can extend polynomial chaos for both multi-fidelity and gradients. And doing this, we can get the AP accuracy at another 2 to 5x fewer high-fidelity simulations. And then also we can find optimal layouts with 3x or so fewer simulations. And finally, I've showed you how we can use this whole thing for different large wind farm AP computations and optimizations. And if you put together the benefits of both of those, we can get anywhere between like 10 and 50x fewer simulations than the current methods used. And this is really helping us go towards enabling high fidelity computations for these type of problems. What's exciting here is actually, I think, the amount of future work that is available. So I think once the problem's been formulated in the UQ way, we can really start thinking outside of the box. We can start thinking about probabilistic weight models. I got a little bit to that about changing the weight parameter, treating that as an uncertain variable. We can include more uncertainty, and the problem itself has a lot more uncertainty. As I said, there's the turbulence intensity, and a lot of other quantities, and I showed how it's scaled. Well, it won't scale indefinitely, but at least to 3 or 4 dimensions, Polynomial will do better. And then if people are starting to develop gradients for the weight models, not just with respect to the design variables, but also for the uncertain variables, you can incorporate those into the UQ method as well. Another thing is to try out with a high fidelity CFD and see how well these optimizations actually work. And our collaborators are hoping to go there. And another interesting problem is that I kind of like put on the side is really I'm assuming the input conditions someone gave me are correct. And then I think that's also you need to properly characterize the wind. And I think that's a big area of future work. Okay, so that finishes, I guess, the technical part of the talk. Okay, so one thing I really like about the Aeroastro department, I don't know if it happens in other departments, is people get to acknowledge people. I don't know if this is a thing about other departments, but I like it, so I'm going to take the opportunity to do that. So first, the committee. Professor Juan Alonso, I guess, who I hope to become. No. Don't go there. No, but thank you so much. It's great working for you. It's very, if I'm always smiling, I guess so are you. So that is very nice. And you've been very, let me free explore kind of whatever I want. And then always when I'm confused or something, then make sure I go back in a good direction. So I always like to think is like if you give someone enough rope, it's like you give enough rope to somebody they can hang themselves. But then you realize, oh, the rope, you still had a lot more rope. Actually. So there was no problem ever long. Everything was under control. So you keep us all under control, so thank you for that. Professor Iacarino. So when I just came to Stanford, I remember going to, it was like a UQ workshop or something, and I was like, oh my God, there's uncertainty in the simulations, and I just got so excited, and then taking your class, and I think it started me down this path that will probably continue. Like every time there's a simulation, I was like, okay, but there has to be uncertainty, or I think the first time I said, well, there's no error bars. Like no one ever puts error bars on simulations, and they should. And I think since now a lot of people are doing that, I think a lot because you've been preaching about this for a while. So you've been a great inspiration. Michael, as well, you incorporate uncertainties in a lot of problems in a slightly different way, but it's very exciting. And I also, I just like how much energy you have. It's incredible. I don't know how you do it, and always in a good mood and always willing to help. Professor Enge, thank you so much for being here. I've always had good experiences every time I've interacted with you and quals and everything, and so I really enjoy it. I also want to thank you personally for letting us use the ping pong table. So, and one day I'd like to see both of you play, I guess. Exciting. Like I love how you just look at problems and just look at them in a completely different way. Some people might not be familiar with Professor Dabiri's optimizing wind farms as well, but looking at it from a complete different perspective, well, and actually using different types of wind turbines as well, vertical axis wind turbines. And I'm happy you're at Stanford now. I briefly met you a long time ago. I don't know if you remember. but at an APS conference I went as an undergrad. But it was, you showed up to my presentation and I was like, oh my god. Oh undergrad, I don't know what I'm going to do anything. Yeah. It was great. Yeah, it was great. I don't know, but yeah, I'm feeling better now. But thank you so much. Then there's the collaborators. A lot of the help I got from Mike, who knows basically everything you need to know about quantum mechanics. Collaborators we're working on now recently in this project, Andrew Ning, and the students at his lab, Jared, PJ, and VG. People I worked with previously were quite helpful. Karthik, Francisco, and Tom. We haven't worked much lately together, but these people were very helpful to get me started. I also wanted to thank, I guess, well, first all the Eurastro staff, they're great. And then sponsors. I was lucky to come here on a graduate fellowship, and then through the help with, I think Mike had something to do with this one, but but I'm very happy I got the Sandia National Laboratories and Stanford University Excellent Engineering Fellowship, and lately working on this National Science Foundation project. So then there's friends, of course. It's really nice to like come to a place where you have lots of friends, and it's so nice. Like, I know some people are not in these pictures, but thank you all. So we have a soccer team, our ADL soccer team. Unfortunately, we lost last week, but that's good because otherwise we would have played last night, and I don't think that would have been a good idea. So thank you for losing last week. And then this is in front of Durand, and this is just shows like how much camaraderie there is between all the Eurastro departments. So I have lots of friends in the Eurastro department, and thank you very much, and other friends. And finally, family. I don't know if that's being live streamed, maybe, but so thank you so much. I don't know what I want to say here. Maybe I'll tell them personally. But I do want to acknowledge my brother here. We did go to the World Cup to support Ecuador, and he came out specifically for this. Well, not specifically for this. He has a conference in Berkeley, but I don't really have this is my grandparents, who people lately or been asking me like, so okay, why did you do the PhD and all of this? And I'm trying to figure out like where a lot of the motivation came from for actually like studying and material school. And I think it comes from my grandparents, and I think this is me leaving Ecuador without knowing where I was going to end up. But I'm happy I ended up here. But yeah, my grandma was one of the first women to graduate with a science degree at the University in Ecuador, and she faced so many troubles, and she always pushed forward and showed how important education is. My grandpa passed a few years ago. Sorry. and like I guess normally you say when you have a newest addition to the family is a kid, but there's no kid yet. I'm happy to be starting a family with you. No kid yet, so. But yeah, thank you everyone. And I'll take any questions.
All right, thank you. Questions from the audience. We'll ask the committee that the committee reserves their questions for the closed session. So, any questions for Santiago?
What are the difficulties that you'd expect in implementing this in 3D? So either the constraints with like uneven terrain, or as a variable of setting them at different heights.
So, as for in the uncertainty quantification part, it's fairly straightforward to add a different uncertainty, like, well, let me back up. So there was going to be a lot of difficulties if we want to be able to model that properly. So in the model itself, we would need to use different models. Well, we could use the high fidelity models, TFT, that will account for that. We'll have a grid that makes sure we have the different height. Or we can use the lower fidelity models and you tune them in a certain way that you incorporate sort of these 3D effects. If you want to consider the terrain, let's say, even with these two models, but as an extra uncertain variable, you could do that fairly simple in the problem. If you have some sort of distribution that you want to figure out what the layout or the height of the terrain is going to be.
Any other questions?
Let's say you changed your objective function to be the cost divided by the AEP, and you wanted to, instead, you could have like up to a maximum number of wind turbines available. How would you think that would change your optimized layout? Do you think you would still use all 60, or would you have 45, or?
So you think, given the same constraint area?
Right.
So it's a good question. So that constraint area is being, so the turbines I used an open source model. They're 5 megawatt turbines. The larger that area that's constrained, that's built, the turbines are 3 megawatts, so they're smaller. So maybe actually there's too many turbines for that particular layout. So it could be less, but I don't know. There are some optimizations where people will run where it's like a design variable is really the number of turbines, like how many turbines you put, or the type of turbine. But one thing I've learned is like it's fairly unintuitive to figure out what the good layout would be, especially if you run the problem considering all wind speeds and wind directions.
For a given area, there's probably a maximum number of turbines that,
Yeah.
that if you keep adding turbines, the cost goes up and the energy production doesn't, right? So I wonder.
Oh, yeah.
Is that what you were asking?
Well, I mean, depending on how much they cost to build, would he expect, I don't know, 45 to be built early? I don't know,
So yeah, one of the things, the cost model is as well is like a huge uncertainty in wind turbine. Like if you're going to build a large wind farm, you need to take a big loan. There's a lot of uncertainties in what the energy prices are going to be, and like so a lot of people are trying to actually model the cost better. So you can use multiple fidelity of cost models as well in the problem.
So adding in, or you're adding a bunch of uncertainty, would this be scalable to multiple types of wind turbines in a wind farm? So, Professor John, he's using vertical wind turbines, so would it be possible to add those plus your traditional wind turbines in that same model?
As long as you have a wake model or something that can compute the power, yes. So as long as we can compute that efficient, or we get an estimate that's correct, yes, we can add it. If we're trying to figure out, if you have a fixed number of them to start with, it's easier if you're trying to figure out which one to pick, then the optimization problem becomes sort of, you have a binary choice, so it becomes a harder optimization problem.
Any other questions?
So the existing wind farms appear in your slides, you showed that they're mostly gridded.
Yeah.
And maybe I'm wrong about this, but is the reason for the gridding to minimize the cable length? And if it is, then sort of these random layouts where you have these really highly optimized layouts for AEP, but they end up sort of reducing your cost of energy because you have sort of really high investment costs.
So there's,
cabling.
so some optimizations with the collaborators that have increased cable length, but so introducing cable length is kind of like introducing a cost in some sense. I think there's definitely potential to move away from the grid-like layouts. People have been building these because they're fairly simple, and a lot of the original studies were done here, and then you just like, okay, let's put them as far back as possible. And a lot of times, a lot of sites have very directional wind as well, so even if for one direction they're in a grid, it's not too bad. I still think that you would, I don't know if you add all the cost constraints, like how much it's going to change, but I still think there's potential to have the layouts not in the grid. And one of the things of not having in the grid, again, as I showed, it becomes, if we're trying to model this, it becomes actually easier.
Any last questions? next. So this completes the public portion of the defense. We're going to take a 2 or 3 minute break and